Hello everybody, welcome back. In this lesson, we will go over the next rule of differentiation, which happens to be the last rule in our formula sheet, or in other words, the last rule in our recipe book. And you will be surprised by combining these just handful of rules together with like one side of a page of a formula sheet. I mean, it's not too complicated. With that simple content, you can compute pretty much any derivative. You can do any differentiation computation, and this is the last step that we need to have in our computation. So the chain rule is none other than the derivative of a function sitting inside another function. In other words, this is what we call a composition of functions. So this is a function inside another function. So this is a composition of functions. So when you have a composition, how are you going to take the derivative? You need to recognize the outer and the inner function. So the outer function is what you see as a outer operation, and inner function is exactly what you see inside. So this is the inner and this is the outer. This structure sometimes could be slightly complicated when you have different structures of our functions. We need to recognize that carefully. But once you have the outer function, what you're going to do is to differentiate the outer function and leave the inside argument as it is. So you need to input whatever the inside function right away. And then you grab the derivative of the inner function and you just multiply it together. So f prime at g and then g prime. That is the combination. So let me show you how simple it could be in terms of applications when you understand it. Step number one, recognize the inner and outer components in this scenario. Outer function is right here, sine, and inner function is what's sitting inside the innermost computation. Sometimes when it is complicated to understand the inner and outer layers, this is a recommendation. Try to look at, uh, think about a computation. If I ask you to evaluate this function when x equals 5, what are you going to do first? You're going to plug x equals 5 and you're going to compute the square first, right? You're going to do that computation right at the beginning of x term. So the first computation goes to the inner function. And then you construct these layers and then you come up with computing sine of whatever that computation. So that is the second operation, is the outer layer. So now this is the outer and this is the inner. All you need to do is this. The derivative of sine, we know it is cosine. We know the derivative of sine x is cosine x, but now I'm not gonna write sine x or cosine x here because our inner argument is different. So the derivative of sine is cosine. That's all I'm gonna say. And then I'm gonna open parentheses, and what I'm gonna include here is the original function. Look at this. This is just resembling what we have right there. The derivative of the outer function at the inner function, which is itself is x squared. And then in the next step, what we're going to do is to multiply it with the derivative of the inner function, which happens to be just 2x. That's going to count for g prime in our formula, right? So that's the simplicity of this application. Let's play with one more example. Now in this scenario, you see a different composition. Here you need to recognize the inner and outer. Look at this. The inner component is what you're going to do with x right away. If I ask you to plug in x equals 5, you're going to plug in right there in the exponent component, and then this exponential is sitting out, right? So what are you going to do is to take the derivative of e to the x. But when you take the derivative of e to the x, you know it's going to be e to the x. But here our function is, now you took the derivative. This is not just the original e, it is the derivative e. And when you take it, now you're going to evaluate it at x squared plus x plus 1. And then you need to get to the inner layer. Now you already peeled the outer layer. You get to the inner layer. You take the derivative of x squared plus x plus 1. Do it. You're going to get 2x plus 1 as the derivative of this component. And don't forget to multiply. Don't forget to have parentheses because there are multiple terms here. Otherwise, Mathematics would not recognize your answer if you miss the parentheses. Let's play with one more example. In this scenario, you have 3 layers if you look at it very carefully. How are you going to work with it? It's very simple. This is a chain rule, right? You move your derivative operator one step at a time. Let me show you the practical way of doing it. Recognize the outermost and then take the derivative of that. So tangent, derivative of tangent is secant square, and then you're going to include what's inside that tangent function. So sine ex is what's in. And once you're through that step, now you're going to take the derivative of the inner component, but now you can see again a composition. Now don't forget the tangent, the story about tangent is now over because we're done with the outer layer. Now you need to take the derivative of the inner component right here, but it has another outer function. At that instance, the derivative of sine is cosine, and then just transfer the original function right there. And then times now you are in the innermost layer. Now take the derivative of ex, which happens to be ex. That's your final answer. Now, this is an example where you can really see the meaning of the chain rule. It is a chain application. It is not like playing with two functions. Now, let's say you feed one function in another and you keep doing this process until up to 100 steps. If you do that, you're going to unwrap one layer at a time and you will do the same process one step at a time. So that is the power of this tool. Now, let's play with some easy example in this scenario. Look at this. I'm asking you to compute two different derivatives. If I ask you to compute this component, now there are two ways of doing this. You can just FOIL this first. When you FOIL it, you will end up getting just 4x squared plus 20x plus 25 after FOILing. And then what you're going to differentiate is just a polynomial. You can do that. However, when you know the chain rule, you can do it easily. Look at this. The outer function is this square operation and the inner function is what you see right there. So the derivative of, let's say, like if I pretend this to be x, I didn't cross it out. I just pretended it like bigger x, right? So if I consider x squared, the derivative is supposed to be 2x to the 1, right? But that x is exactly what's sitting inside. So let me do this. I have to be careful with removal of this without removing anything else, right? So x is none other than what's sitting inside. So what you see here is just like playing the role of, like, let's say if you name it like a different variable, and then times, don't forget, now you need to take the derivative of the inner function, which is going to be just 2. This 2 is coming from the power rule. This 2 is coming from the derivative of the inner function. Now, look at this example. When you take the power to the 10 of a binomial, here also you can expand it to a polynomial if you like. But well, good luck with that, because it's going to be a tedious computation, which I'm not planning to do. Instead, let's use the power rule. Let's use the chain rule right away. So when you use the power rule or the generalized power rule or the chain rule in this scenario, look at this, the same thing. If I pretend this to be my big variable, so 10, whatever that term right there, to the ninth, n minus 1, right? N x to the n minus 1. And that x is now supposed to be nothing other than the original function sitting inside, and then multiply it by the derivative of the inner function, which happens to be just 2 times 2. The simplification that you can have here is like these two constants can be combined. It's going to be 20. You can write it in front. The same thing could be done here, but it's totally up to you. So one more example, let's do this. In this scenario, we do have this function. Now, you can use the quotient rule if you like. But if you look at this very carefully, some quotient rule problems can be converted to power rule problems. And in this scenario, inside the power, you have a different function. And this is 5 is in this case none other than a constant multiple. So I will bring it out. So 5 times. Now take the derivative of this component. That is nothing other than exactly what you have seen already. So the power rule. So negative 3 x cubed minus x plus 2 to the negative 4th power. Check how we got that. That is the outer layer of the chain rule. And then the derivative of the inner component 3x squared minus 1. And that is our derivative. And there are simplifications that you can have since these are multiplications. You can gather these two. If you want, you can write this one in front other than having it behind this power term. So either way, those are just simplifications and not the most important. The most important is to get to the derivative computation correctly. So some easy computations to conclude our lesson. E to the 5x. Now we know the derivative of e to the x is going to be just e to the x itself. Now here in this scenario we have pretty much like, let's say, e to the 5x as it is, because the derivative of e to the x is e to the x. So now e to the 5x should have similar output. And then it is not complete until you put the derivative of the inner function at the end. So the same thing here, the answer for this one would be e to the negative 10x times negative 10. The derivative of the inner function is none other than just negative 10. And the answer for cosine of 10x plus 1, the derivative of the outer function is negative sine of the inner function at the inner function. So 10x plus 1 and then times 10, which happens to be the derivative of the inner function. And then when you take the derivative of secant x, if you take the derivative of secant x, it happens to be secant x times tangent x. Now, it's interesting, in this scenario, the inner argument appears twice because secant x times tangent x. Now, since our inner argument for the outer layer of the derivative of the chain rule is supposed to be the original function, 5x will appear here, 5x will appear there. And then right after that, you're going to grab the inner function, take the derivative. All right. So that brings us to the computations related to the chain rule. And with that, we conclude the session related to the chain rule. So I will see you in the next lesson where we are going to have different level of derivative computations by mixing up all of these different rules and tools. I will see you in the next lecture.